Hello everyone, now I want to discuss how we're going to start fill those electrons in those orbitals, and that involves the Aufbau Principle. And usually as before, we have to recap, and the previous section we discussed about the Schrodinger's quantum mechanic model of atoms. As you can see, it's illustrated here. With a positively charged nucleus. Now it's being surrounded. It's being surrounded by principal energy levels. Those n equals 1, 2, 3, 4, 5, 6, and that is pretty much the Bohr's model. And Bohr stopped there, and he didn't go further. His model worked for hydrogen only, and the helium broke down. So it came in, that comes in the Schrodinger. He introduced some finer features on those principal energy levels, what we call the sublevels. On n equals 1, you have 1s. N equals 2, you have 2s and 2p. N equals 3, you have 3s, 3p, and 3d. N equals 4, 4s, 4p, 4t, 4f. And the list goes on and on, as you learned in the previous sections. Those are determined by the three quantum numbers n, l, and m. Particularly the L number dictates the sublevels S, P, D, F, and on those sublevels, then the m quantum number value will determine how many orbitals you have. As you can see from here, the concept of orbitals we're going to discuss later is essentially a three-dimensional region. It's the probability. You have a 90% level of confidence you will find certain electrons with that certain energy there. And for the S sublevel, you're involved with one. You only have one orbitals, is one box. For all the S sublevels on the different principal energy levels as indicated by those numbers, only one orbitals. For the sublevel P associated with L equals 1, and now you have three orbitals, and those three orbitals will be of the same energy. D, you have 5. F sublevel, you'll have 7, and G sublevel, you'll have 9, and the list goes on and on. So now we have this essentially distribution of how those orbitals are distributed. And before we can actually fill those orbitals with electrons, that's our ultimate goal, we have to talk about each of those orbitals is represented by a box, and each of those boxes can only have 2 electrons spinning at opposite direction. As we discussed about that before in the Pauli exclusion principle broadcast. As we said, electron, they repel each other. What to hold them together in a tiny space, we call it orbitals, is the magnetic field generated by the moving electrons. So they have to spin in the opposite direction in order to generate north-south, south-north combination. The strong magnetic attraction overcomes negative repulsion. So this is essentially Pauli exclusion principle. Okay, based on the Pauli exclusion principle, then we will have the maximum number of electrons that can be put on S, P, D, F, G, H, I, those sublevels. As you can tell, S, you only have 1 orbitals, so the max number of electrons will be 2. P have 3 orbitals, that will be 6. D have 5 orbitals, that will be 10. F will have 7 orbitals, 14, 18, 22, 26, and the list goes on and on. So now we start knowing how many electrons we can, maximum number of electrons, and we can actually put onto each individual sublevel. So now we are moving, inching together for the feeling for how we take those electrons, how we fill them up in those orbitals. Before we proceed any further, and it will be a very interesting question to ask. And if I happen to have a beaker, okay, that's just a cool draw of a beaker. If I start pour water in it, okay, so what would the water go? Let me use a blue pen to represent water. The water will fill the bottom first, and as more and more water come in, you're always going to fill from the bottom to the top. And here comes, you do not see any gap between those water, between different portions of water. Why? Because those gaps are not allowed. And this is actually an illustration of another very important principle. We call it Aufbau Principle. It simply states, when you fill the electrons, you're always going from orbitals with lower energy first. Fill them up, then go on to the next one. Next orbital. Okay, so this is quite analogous. If we say it, this is quite analogous with that, fill any container with water from the bottom up. So if we can actually rank those sublevels as we indicated before, or even the orbitals in a sequence from the lower energy to the higher energy, we actually can have the sequence how those electrons can be filled in. So I want to do an interesting exercise, and let's reproduce this schematic illustration of Schrodinger's model in a different way. And as we know it before, closer to the nucleus, lower the energy. As the Bohr's model is also true as the Schrodinger's model. So then we're going to reproduce that in a different manner. And what we're going to come here is, at the bottom, we're going to have n equals 1. And then we're going to have n equals 2. We're going to have n equals 3. Then we're going to have n equals 4. We're going to have n equals 5. N equals 6. And n equals 7. And the list goes on and on. Further away you remove it, higher it gets, the higher the energy. That's the schematic illustration on that. So on the first principal energy level, you'll have 1s. Sublevel on 2, you have 2s, 2p sublevel, 3 you have 3s, 3p, 3d sublevel, 4s is 4s, 4p, 4d, 4f, 5s you have fifth principal energy level, you have 5s, 5p, 5d, 5f, 5g. Later on, you'll learn the G and the after sublevels are not needed when we have the ground state electron configuration for all the elements on periodic table. However, they are all there. They are ready to take electrons if needed. 6, 6s, 6p, 6d, 6f, 6g, 6h, 7, 7s. 7p, 7d, 7f, 7g, 7h, 7i. And I also like to draw a straight line here, as indicated this is moving away from the nucleus. It's further expanding it out. And if you're looking on here, it is very clear. 1s should have the lowest energy. That is closest to the 1s sublevel should be the closest to it. And then you're now following on to the 2. So between the S and the P on the 2, which one should be lower? And according to Schrodinger's calculation, the off-bounds calculation, should be the 2s. Okay, 2s is the next lowest one, and you have a 2p. Logically, you move on to 3s and 3p. This is where situation get a little bit interesting. According to the calculation, quantum mechanical, the theory calculation, the model calculation, instead of 3D, and now I have a 4s coming. The 4s sublevel, the 4s orbitals are closer to the nucleus compared to 3D. The next one will be 3D, and next one will be 4p. So, but however, instead of 4D, then you go for the 5s. Then you're going to get to the 5s. You're going to get it's going to get 4D, and this list goes on. Now you say, like, wait a minute, this is a bit too complicated actually to memorize. Here comes a very interesting way of dealing with that. Someone came up with this brilliant idea, and I will show you graphically how. Okay, so just reproduce that and lay them out, and n equals 1, 2, 3, 4, 5, and all the sublevels. And now you start to draw the diagonal arrows. You can draw diagonal arrows. Then you hit the wall, you're coming back. You hit the wall, you're coming back. So what it does means is you follow the arrow, you follow the sequence. You start with the here, and you follow with that. You can do 1s, you hit the wall, you're coming back, and then you start with the next arrow. You have 2s, hit the wall, you're coming back, there will be 2p, 3s, and coming back will be 3p, 4s, and coming back will be 3d, 4p, 5s, and the list goes on and on. You can literally reproduce all of them in the proper order. As you can see, after 4D, then that will be 5p, and after 5p, that will be 6s, and after 6s, that will be 4f. You can see this is an interesting observation. You go to the 6th ring, 6s, before you can coming back to 4f. As you can remember, the maximum number of electrons that can be held onto each sublevel. In this case, the S sublevel will be 2s. The P sublevel will be 6. Okay, and the D sublevel will be 10. And S sublevel will be 14. And this gives us the guide for how those electrons are going to be filled in. And this is giving us the guide if according to the Aufbau Principle. It is a bottom up, and it gives you lowest possible energy that are associated with those electrons. And there's a terminology for that, and that is called ground state electron configuration. Is how those electrons can be filled with those sublevels, the orbitals, in the least energy that is possible. So the next, we're going to take a look at how this is put in the Aufbau Principle coupled with the Pauli exclusion principle and all this sublevel, the orbitals, and how we start putting the electron onto those orbitals. And let's take a look at what we have. If we have hydrogen, we're going to have one electron to handle it, and we can recall the first lowest energy level, a sublevel will be 1s, and you need one electron to be placed on that. So this is 1s is the sublevel, and 1 will be the electron. So the helium, you have 2 electrons to put on, but a 1s to start, you know, on 1s can actually take 2. So we stop there. We're done. It is all the electrons are filled up. All the electrons are taken care of. Lithium, 3 electrons. You have a 1s2 now. Can you do 1s3? Can't, because of Pauli exclusion principle. And now you're going to 2s1. And as it goes, and just keeps on moving on. And let's see, carbon, we have 6 electrons, and we're going to have 1s2, 2s2, 2p2, because there are 2 left. So for nitrogen, 7 electrons, 1s2, 2s2, 2p3. Remember, 2p sublevel can take more than 2 electrons because you have 3 orbitals. You can max out at 6. Okay, you max out at 6. And the oxygen, you will have 8 electrons. Then you can keep on going 1s2, 2s2, 2p4. Fluorine, you have 9 electrons. 1s2, 2s2, 2p5. And you can hopefully you can quickly get a hand of it. And now we can put it in the calcium. Calcium, according to the periodic table, 20 protons. Calcium atom, you should have 20 electrons. And now have 20 electrons. Then you have 1s2, 2s2, 2p6. Now move on to 3s2, 3p6, and count them: 2, 4, 10, 2, 6 is 8. The next one will be 4s, and this will be 4s2. And all those is what we call the ground state electron configuration for element. And basically, you got to apply the Aufbau Principle. You always fill them from the bottom up. Let's take a look at one of the other specific problems, and now I can ask a lot more questions. And in this case, it's for sulfur atom. As its ground state, we have to specify that. How many principal energy level does it have, and how many sublevels does it have, and what is the sublevel with the highest energy, and how many electrons are on the sublevel with the third highest energy. It's really, that is mindful of questions. How do you get started? And it's always start with the ground state electron configurations. And you take a look at sulfur on periodic table. You have 16. Now this is 16. Okay. So you have 16 electrons, atomic number 16 electrons. Then you can start to arrange them. It will be 1s2 of one principle, 2s2, 2p6, 3s2, 3p4. And this is 2, 2, 4, 6, 10, and 16. So this is the ground state electron configuration for sulfur atom. And how many principal energy level does it have? Then you have equals 1, 2, and 3. So answer for this part is 3. How many sublevels does it have? What our sublevels are? S, P, D, F. And you have ground state electron configuration. Simply count them. How many of the sublevels have the electron on them? 1, 2, 3, 4, 5. So you have 5 sublevels. What is the sublevel with the highest energy? Remember, Aufbau Principle, the last one. So then that will be 3p. is the one with the highest energy. How many electrons are on that? That will be with 4 electrons. Okay, so if this is the highest, what will be the second highest? 3s. And what will be the third highest? Will be 2p. It's the sublevel. And how many of the electrons are on there? And you should have 6 electrons. As you can see, as soon as you can establish the ground state electron configuration for the element, you can actually have lots of questions asked based on that. So this is the key, the first key step. Write down the ground state electron configuration. Then you have to understand what the question is asked. I can ask you about the sublevels, I can ask you about the orbitals, I can ask you about electrons. Okay? And the last concept I want to go over in this section is, let's bring back the sulfur. Let's see sulfur. The ground state electron configuration, we have 1s2, 2s2, 2p6, 3s2, 3p4. As you can see, this is the first principal energy level. Now those are the 2 sublevels on the second principal energy level, and this one will be on the third principal energy level. What I want to introduce the concept about is the circular plot. As we can see before, what will be the charge on the sulfur nucleus? Sulfur nucleus has 16 protons, so you have to have the charge of plus 16. And now we start drawing those pictures very similar to Bohr's model. And what we've talked about, principal energy levels, and this one will be n equals 1, this one will be n equals 2, this one will be n equals 3. Now we use a dot to represent electron on it. So on the first principal energy level, there will be just 2 dots. If I can get those dots on. For the second principal energy level, we should have 2 plus 6, that should be 8. 2, 3, 4, 5, 6, 7, 8. For the third principal energy level, we have 2 plus 4, we should have 6. 2, 3, 4, 5, 6. So this is a circular plot. You're indicating the charge on the nucleus and also the principal energy levels, and each one of them will have different number of electrons on. This is actually brings in a very interesting question. For the first ring, for n equals 1, the first ring, the innermost ring, what will be the maximum number of electrons that can be on there? For the first ring, you have 1 sublevel, 1s, it's 1 orbital, 2 electrons. Okay, so for the second ring, so you have what? 2 sublevels, s and p, 4 orbitals, and you have 8. For n equals 3, mind to take a guess, that would be 18 electrons. And for n equals 4, and that would be 32. So the formula goes by is maximum 2n squared electrons for each principal energy level. So for the maximum number, you can draw it on each ring. It depends on which n you're talking about. Learned the Aufbau principle and the sequence of how those orbitals should be filled up. And we started with the sublevels and the 1s, the 2s, the 2p, and be careful about how those the sequence, because between n equals 3 and n equals 4, that sequence was off. 4s has lower energy than 3d. Okay, so then with that I conclude this podcast, and thank you very much for your attention.